Thank you very much for coming. We're very lucky to have Professor Miguel Anjos. He was actually visiting
Anjos.
Anjos.
Portuguese.
Yeah.
That's right.
Remember,
Tito knows all about that.
Yeah. He was visiting Universidad Católica and other places here in Chile, so we're lucky to have him in the seminar. He offered himself to do a talk here, so we're very lucky.
With much pleasure.
He's a full professor and Canada Research Chair at the Department of Mathematics and Industrial Engineering at Polytechnique, Montreal. And he'll be talking today about the unit commitment problem. We've been working a lot at that. So thank you very much.
Okay. Thank you very much. It's a pleasure to be here. Thank you for having me. We were just talking about French connections. I'm now also formally affiliated with INRIA in the context of what's called an international chair, which is a 5-year research program for collaborating with people at INRIA, so on issues of energy as well, which is a thing that they want to grow. So giving the seminar in French might have been an option, but it's probably better to stick to English. I'll, as Rodrigo mentioned, I'm going to speak about the unit commitment problem. The unit commitment problem basically has to do with making decisions about the cheapest way to generate power to meet the load, to meet the demand. So if we look at this picture here, this is time of day for 24 hours on the x-axis, and on the y-axis we have the load at each hour of that day, the forecast load on a day-ahead basis for that day. So this curve basically says, for example, that at 6 a.m. we're expecting to have a load of somewhere between 1 and 200 megawatts. These are obviously just made up numbers. And then it goes up. You have a peak in the morning. It drops a little bit. You have a second peak in the day, and then it drops off again at night. This is very roughly what a real load curve looks like. So what we want to do is to make up a schedule of which generators should be on and off at each hour to produce enough power to meet the demand. Okay. So the basic idea would be to do something like this. Let's suppose I have 3 generators, one that can produce 200, one that can produce 300, and one that can produce 400. So what I want to do is to use those rectangles that represent the power level of each generator to cover the area under the curve. So this would be one way to do it. So here I have a load that's a little bit under 2, so I turn on the generator that's of capacity 200, and I'm fine. Here I would go for the 300, and so on. I pile them up during the day. What I'm trying to do is to minimize essentially the area that's generated but not within the curve, right? I want to get the closest fit to the area of the load curve to actually cover this area. Now, that's one thing, but the next requirement is that I can turn it off before the 4th hour after that. So in this solution, the color is not coming through terribly clearly, but for example, here there's generator 2 that's only on for 2 hours and then off again, so I can't do that. And there's another one here that's only on for 1 hour, and so this would not be an acceptable solution because of that constraint. I also have minimum downtime. If I turn a generator off, it has to stay off for a certain amount of time. So again, there are some places in the schedule that don't satisfy those constraints. So I want to basically find the minimum cost solution to schedule generation to meet the load subject to the various conditions on reserve and on the operating constraints of the generators. This is what I just said. We want to minimize the system-wide cost to meet the demand and also to ensure safety. So here we're basically talking about the various operating constraints and reserve. This problem is very important in practice because even if you make a very small improvement in the solution quality, this is being solved every day. So your very small improvement translates into a lot of money very quickly, because this is being done repeatedly. So it's a problem that's attracted a fair bit of attention, and that is certainly very relevant in the power industry. As a consequence, there's a vast literature on this. One of the early techniques that was used to solve this problem, this is a large mixed integer linear optimization problem, as we'll get to in a moment. One of the early techniques that was used for a long time was Lagrangian relaxation, which you would basically run as long as you could and get the best solution that came out of that. With the improvement of software and solvers, we now, the standard in the industry is to use mixed integer linear optimization. And basically, most of the time, the solver stops fast enough that you can get an optimal solution to within a pretty small gap. More recent work is looking at things like semi-definite optimization, which is essentially a generalization of linear optimization to general nonlinear cones from the non-negative orthant, and the addition of extra requirements from the operational perspective, which brings in stochasticity and robustness and other such concepts, because now that we have the computational power to solve what we wanted to solve before, well, now we want to do more. This is the constant theme in these kinds of things. And there's a book that was published now 15 years ago, but it still has a very good picture of the problem and the main challenges. Several of them still being worked on. That was edited by Ben Hobbs and co-authors on this topic.
Excuse me, another question?
Yes, of course.
The load curve, how
Yes.
much it varies from day to day?
That's a good question. Typically, it doesn't vary a lot for similar days. So it will vary, within the week it will vary. But within Mondays, from week to week, it tends to stay reasonably similar, but it will change over the year with the season as well. So there's variation within the week, and then there's variation within the year for the same weekday. So you still have some variability in the load curve. But that is an important point, because one of the aspects that can help solve this problem in practice is the fact that you can often use a previous solution to re-optimize more quickly. But not necessarily yesterday's. You have to pick a good starting point. Yeah. Okay. This is a very simple way of expressing the problem as a mixed integer, not a linear problem. So we want to minimize this sum of the costs. So this is sum over all the time period and sum over all the generators of the cost of generation for that unit times the amount of power that I'm producing. Okay, so very straightforward. subject to the constraint that the sum of all the generation at each time period has to at least meet the demand. And then a bunch of additional constraints that take account of run uptime and run downtime and ramping and other such constraints and security and so on. So the effective function is fairly straightforward. Generally, these costs are assumed to be convex quadratic, meaning that the more the output grows, the more expensive the next unit of power gets from the same generator. But in practice, they can be approximated using supporting hyperplanes, and this works very well. So there's no great challenge there. Demand must be met, obviously, is easy. The hard part is getting the expression of these requirements. So that's what a lot of this presentation is about, working on the description of the operational aspects of the problem. We're going to need binary constraints, and let's start with defining those for the problem. The way this formulation works is that we're going to have for each generator 4 variables, 3 that are binary and 1 that's continuous. The continuous one is the actual amount of power generated, and we're going to assume that it can vary continuously within certain bounds. The binary constraints are going to tell me at each time period for each generator if it's producing or not, if it has just been switched on this time period, and if it has just been switched off this time period. So knowing when it's switched on is going to help me make sure that the up and down time constraints are respected, and knowing if it's producing or not is going to tell me if I can produce, if P has to be 0 or not. Okay. That's basically the idea. If you think about this for a moment, you realize that you don't actually need all these variables. If you know some of the information, for example, if you know all the V's, then you don't need to know you can deduce the Y's and the Z's. And we'll talk about that a little bit more in a moment. Let's stick with those variables for now. How are we going to write these constraints? Well, the first set of constraints is that there's maximum and minimum power limits. If a generator is on, it has to produce within a certain range. And these constraints say that, well, that production has to be bounded by some lower bound capacity times the V and an upper bound times the V. So if V is 0, then P has to be 0. And if V is 1, then it has to be between the bounds. Right? We have ramping constraints that say if a generator is on, it can't change its output too fast. We can't arbitrarily increase very rapidly capacity to the production or decrease it very rapidly. So that's what these constraints say. They basically bound the change one way and the change the other way over from one time period to the next. So the difference in the P's, both in terms of increase and decrease. So if you're going up, then you can't go up by more than a certain amount, which is the ramp up. And you can't go down by more than a certain ramp down limit. Plus, these startup and shutdown amounts that basically say if you want to get a generator to start up, if it's at 0 and it goes start, then it cannot start at more than this amount. That's the maximum amount in the first period that it's on. And then it can ramp up using RU. And the same thing the other way. If you want to shut it down, you have to get it down to this shutdown amount. And then you can turn it off. You can't just turn it off from a very high point. So it's basically forcing limits on how fast the output can change. And then the third set of constraints we're going to look at are these minimum up and down time that I've already mentioned. So if we look at the first one, it basically says if I switched on the generator at a certain time k, then the sum of the V's from that time onwards has to be, they all have to be ones for UT periods. So it has to be on for minimum uptime. And if it's just been switched off at k, then a bunch of the V's have to be 0 for a certain number of periods. So you put all this together, and you can solve the problem, and you get a certain performance, and then we start looking at questions such as, can we improve the efficiency of the formulation? So we have a correct formulation, but one question is, can we do better? So one interesting piece of work was done by Rajan and Takriti in 2005 that basically looked at these minimum up and down times. So I'm going to come back just one slide to these ones. So these are the ones we're looking at. Okay. I was saying the sum of the V's all have to be 1 or 0 for a certain number of periods, depending if I've turned on or turned off. These are the same restrictions, but expressed in a different way. So what these basically say is now that you force the V to be 0 or 1 for an individual time period based on the Y's and the Z's. So it's a different way of expressing the requirement that it has to be turned on. So if it was turned on within the last UT periods, then the corresponding V for this period has to be 1. It's expressing things a bit differently. And the same thing, if you just turned off within the last DT periods, then this V is going to have to be 0. You're going to have a 1 in here. This whole thing is at most 1, so this guy has to be 0. Exact same constraints, but expressed in a different way. One of the things that's nice about this is that unlike the previous expressions of these constraints, if you define what's called the minimum up-down time polytope, which is the convex hull of the integer points, but only taking minimum and up-down time into account, then these inequalities are facets of this polytope, whereas the other ones are not. So from a polyhedral perspective, these are more attractive. And from a computational perspective, they actually work better, as we'll get to in a minute. Another change that we can do is to say, well, we don't need all these variables. Let's eliminate a whole bunch of them. And this was done in a paper also about the same time by Carrion and Arroyo in 2006, where they come up with what they call the efficient formulation, which really means we throw out a whole bunch of binary variables that we don't need. And the details are not very challenging, basically. You can figure out how to rewrite everything with fewer binary variables. There's nothing very complicated about it. But it is a different way of trying to improve things. So, of course, these papers have the ideas, they report computational results, and the instances are not all the same. One of the difficulties here is that there isn't really a benchmark of instances, because this information is usually confidential. So companies aren't going to tell you the features of their generators in general. So you have to generate data randomly in some way. Yes?
For this up and down constraints, you wrote them in some sort of aggregated way. Couldn't you write just in a disaggregated?
So disaggregate where? These ones here?
The previous one.
The previous one? Oh, this. Yes, you could. Well, yeah.
If one k is 1, then the next and the following, they all must be 1.
This is saying if one of these is 1, then no. This is saying all of these have to be 1, so you could disaggregate them. Yes, that's true. You could disaggregate them as well. I suppose part of the trade-off is also that you don't want to have too many constraints. Yeah. So we could try it. We haven't tried it. That's a good point. It could be tried. But the argument that I would make is that it probably, well, maybe they might be interesting if they're also facet-inducing for the polytope, which they probably are. But whether they would help, I don't know. That's a good question. Yeah, you could certainly do it for these ones, and for these ones as well. Yeah, and you would get rid of these coefficients. But that would make your counters a little bit. Yeah, but that works. A bit more complex. That's good. It's good suggestion. I don't think that, at least in the published papers, I don't think I've ever seen that per se. It's usually in some kind of aggregated form. So what we did here is generate a set of data that makes sense according to some rules that are generally agreed, and then just ran the three formulations. So the basic one as I presented it, the one with a reduced number of binary variables, and then the one with this new facet-inducing inequalities using CPLEX 12.1 when we did this, and a cutoff of 2 hours for these MIPs. And the computational results basically look like the following. This is the number of generators in the problem on the left. So it goes from 27 all the way to 53. And as you increase the number of generators, you also have for each one of them the time and the number of nodes in the branching boundary of CPLEX. And what it basically says is that removing the binary variable seems to be a very bad idea. And using the facet-inducing version of the inequality seems to be a good idea. You get noticeable improvement with respect to the original formulation. So we looked at this and we thought, okay, well, we're going to keep all the variables. That's the first thing. But then this idea of taking the up-down time constraints and defining the up-down time polytope, you can do the same thing for the other constraints. You can define a ramping polytope, and you can define a bounds polytope, so to speak. So can we find better versions of those constraints? Because this seems to be paying off, comparing original and up and down time. So that's what we did. It's a similar idea as disaggregating, but we did something else. We looked about this. And one of the things about having the variables is, of course, that if you have more variables, then it gives you more ways of branching. And maybe some of these branchings are better than others. And so if you eliminate the variables, this can impact the performance because you can't branch on them anymore. And this idea of how to branch we'll get back to a little bit later in the talk. But first, let's talk about the constraints. Can we do things better by looking at the other constraints, as I mentioned? And this is what we did. This was work by myself and my colleague Tony Vanelli at Waterloo, and Jim Ostrowski, who was a postdoc at Waterloo at the time and is now at the University of Tennessee. And we looked at the bounding constraints, and we showed that you can strengthen the upper bounds, and we also look at ramping and show that you can strengthen them as well. And that's what I just want to give you a bit of a flavor of how we did this. And then for all of these strengthenings, we proved that the resulting inequalities are now facets of the appropriate projection of the feasible region of the original problem. So I won't go through all the algebraic details of the proofs, but I'll give you the insight by looking at one of the inequalities, which is this ramp down inequality. So what this inequality says is that if I'm going down in terms of the level of P, then I cannot decrease P faster than ramp down times V plus shutdown times Z. So if I'm shutting down, I have to be down to ST, and otherwise I can decrease by at most RT. So if you think about this, you realize that what you're saying is, well, my P is somewhere between P lower and P upper. Somewhere. And from here, the next level of P can only be at most RD below, because that's this constraint here. So I'm away from the shutdown part at the moment. So that's fine, except this piece is going to kick in at some point. If I'm very close to P lower, so if I'm just about if I've just turned on in the previous period, then I'm actually going to be very close to the bound here. But this constraint still applies. Even though I've just turned on, it's still saying I can't ramp down too fast from there. Which sounds a bit funny when you say it, but it makes sense mathematically. So if you've just turned on, then what you realize is I'm going to be very close here, and in fact my ramp down can't go as far as minus RD. It's going to be bound by the lower bound. And so with a little bit of work, you can write a more complicated expression for the constraint that basically says, if I've just turned on, which is this term here, the first term in the second line, then I actually have this P lower bar that's my limit, and I cancel the RD, and my limit is actually startup minus P, which is, so startup minus P bar, which is this difference here down here. So that's basically the idea. Then you still have another term for the next period. But basically, if you think about various such combinations, you can tighten up these constraints. And the challenge was to find the right combination of terms that gives us facet-inducing inequalities for this problem. So this is one example, but you can do it for the other ones. And overall, what this gives is that we get 5 additional constraints per unit time per generator that were not in the previous formulation. So the advantages of this is that adding them will give us a better balance, which can help reduce the branch and bound trees. That's all pretty clear. The disadvantages is that you have more constraints, so it can make the problem more difficult to solve. And even though a tree is smaller, you may still actually take more computational time, depending on how hard it is to solve each node. So we can try to see how this works. And for reasons of efficiency, in the results that I'm going to present, we only put the constraints dealing with fractional variables at each time. So we do separation. Right? We don't just throw them all in. We treat the constraints aside and we do separation. We solve the relaxation. We find some violated constraints from this big pot. We add them in and we resolve. And that seems to work reasonably well. Same set of problems as before, from 27 to 53 generators. And if we look at the root node, there's the gaps from the previous formulation, which was the one with the improved up and downtime constraints. This tighter formulation, and this is the percentage of the gap that was closed. So it's the difference between the other two gaps as a percentage, to give us a sense of how much we improved the gap. So we get improvements that are roughly the order of 8 to 10% of the gap being closed between the two, which is a good start. And then you actually run the branch and bound to see what happens, and we get that the new tight formulation has certainly lower running times in general. And even though the number of nodes is actually not that different. It is a little bit less, but not that less. So at this point, you see some improvement. This is running with a gap of 0.5% to stop the solver. If we now allow a slightly bigger gap of 1% as a stopping criterion, then we can go for sizes all the way to 186 generators. And now you really see the difference, because the previous formulation starts timing out, whereas the new one continues to run within the 2 hours. And in fact, in many cases, we have the solution at the root node. There is basically no branching. So we just keep cutting at the root node, and we end up finding the optimal solution within 1%. So this shows really that the bound is improving significantly in that sense, and we still have very noticeable improvements at the root in terms of the bound.
So,
yeah,
the column gap tight.
Yes.
Is after adding the root node after adding all the cuts?
Yes.
Okay.
Yeah.
So you should go under 1%. When you have 0, I was expecting to have 1%.
Yes.
And,
these gaps here. That's a good point. These should be less than, so these must be,
maybe that's the gap of the root relaxation, and then you start adding this mid gap from 0 to 9.
But then it would be different because this is the starting point and we start having cuts. That's a good point. I forget. I would have to go check the details. You're right. It's clearly not the gap at the end of the process.
Yeah.
But we've.
So maybe just after one round.
I'm not sure. It may be this is clearly before we start cutting. But what I'm not 100% sure right now is whether we've added some inequalities before we start cutting. That's a good point. I would have to go check the details to be sure. Yeah.
Is Stu, what special about the problem that makes, just at the beginning, just look at the root node already get such a tight, such a small gap?
Here, yeah.
What is special about the problem that causes?
Why is the gap? Where's the bound so?
Even just look at the root node, you already get like
you get very
2%. What is special about this problem?
It's the relaxation is very good. Maybe one thing to say is that of course there's been a lot of research done on this problem, so we know that this is a good way of solving problems. In fact, this MIP approach is so good that it is the standard in the industry. So we're trying to improve something that's already proven itself in practice. People solve unit commitment problems with MIP on a daily basis. So this is
the facets that you mentioned are very effective.
They certainly are very effective, yeah. I'm just slightly bothered by this inconsistency in the numbers, so there's some detail that I've omitted to put on the tables. But yeah, I think the answer to your question is that this has really proven itself to be a good.
What was the gap? The typical gap for the original formulation?
If we go, so without the facets,
yes.
If we go back, I didn't put gaps here on this table. This is the original formulation. So you can see the decrease when we've only added the up-down time constraints from Rajan Takviti. These are times, there's no bounds.
But maybe they got to the true optimal there, right?
This is the true optimal formula, that's why. So I didn't put so this table doesn't have the gaps at the root node.
And those root gaps are against the optimal solution? Is that? Or is
These
it
are the optimal solution. The other ones?
Or is that the best little solution at the root node?
These are the gaps with respect to the final solution at 0.5% of optimality. So once we've solved the problem, in this sense, we go back and we say how good was the original UD relaxation and how good was the tight, and how much did we improve at that point. Yeah. And then in the second one, it's running times and the number of nodes in the branching tree. So that's when we increase here, we get much smaller trees. With, of course, it's with 1% instead of 0.5.
So, Miguel, in the third column, what is that? I missed that.
This one here is the difference between the second and the third column.
Oh, in percent.
But as a percentage, to get a sense of, okay, we've decreased the gap, but how much is that decrease as a percentage?
Yeah.
Even though the gap's already in percent. That's the only bit that's a bit confusing. Yeah. Okay. So the conclusions from this work were that number one, it actually helps to have more binary variables around. This is not the first time that it's been observed. It's something that is known in the mixed integer programming literature. Especially in the case of UC, it helps to have more binary variables. And then the second point is that the new proposed inequalities can significantly increase the quality of the relaxation in terms of the efficiency of solving the problem. This was one piece of work that we worked on with Jim Ostrowski. How am I doing for time?
Still have, if you want, you can still have like 10 minutes.
10 minutes? Okay, I'll go a little bit more quickly on this one. What we did as a second part on this problem
Can I ask you a little question?
Of course.
So this the complexity of the deployment is with the size of with the number of units that you want to scale. There's no.
And with the time period is basically fixed because we're doing 24 hours ahead, so it is the number of units that increases the complexity.
And what happens if you change your time period, for example, from hours to minutes?
It will make it harder because all of these constraints are for each unit for each time period. So whenever you increase the time period or whenever you increase the number of units, that's where the complexity comes. That's very relevant because what is being used right now is on an hour step, so 24 steps during a day. With the fact that this is now being used also to do market clearing, we need to get to smaller time steps. So one of the challenges...
You said it's going to be used for market clearing.
Yes.
It isn't because I come from Europe.
Okay.
And there, all of the markets are interconnected. And as far as I can see, no one is working out the optimal solution.
That's true. This is done at a national basis. And then there's an international clearing on top of that. So there's flows inside the countries.
No, it goes inside Europe.
And then there's flows between countries. Well, it depends on the market. It depends on the market. There are. If you look at Nord Pool, for example, then you get flows within the countries, between the countries. But there are other cases where you have one stage within the country, and then the exports are
But the things aren't worked out that way. They're worked out of money or price. It's a question.
In Europe.
Yes, throughout the whole of Europe.
There's no unit commitment.
The unit commitment is a problem for the owner of the unit.
Ah,
EDF,
okay.
for example.
So, EDF will commit its own units.
EDF will give a set of propositions for the price at which they are prepared to offer units for certain periods of time with some constraints on the ramp up, ramp down, as you said.
And they use that to bid into the market.
They bid into the market.
Yes.
How they got to their bid into the market is their personal problem.
They probably use something like this, but that's their problem.
Yes.
Okay. In North America, this is used for clearing the markets. So the companies have to give enough information about the generators that you can run a unit commitment for the market.
Okay, because in Europe, it's on a 1 hour basis, exactly as you said.
Yeah.
It's moving down to 15 minutes because of the renewable power.
Ah, okay, okay.
And it is on 15 minutes, if I understand correctly, in Germany. When you start to work, what you've described is the day-ahead market, I think.
Yes.
But there's an intraday market on top of it.
Yes.
And there are some very nasty little games being played between one market and the other as to what you bid and what you think is going to happen.
Yeah. So you can gain. So that is one of the issues. Is you can try to gain, at least in North America, you can try to gain by the information you provide, the availability you provide to the system operator that's solving this problem. Yeah. Absolutely, it's similar in that sense, but in North America, this is actually used to clear the markets as part of the market clearing. That's interesting. That's a difference between the two. In North America, also wants to move to 15 minutes, essentially for the same reasons, because we need to have better resolution to accommodate the increased amount of renewables in the system.
The unpredictability on the wind power, particularly.
Yeah. So it's the same issues, but the fundamental difference seems to be that in Europe, then the unit commitment is a company thing that uses whatever it wants to make its bids, whereas in North America, this is actually used for.
It's interesting that Europe, which is a socialist bloc as a rule, is using a perfectly market-based system, whereas you use a political system, a central planning, almost communist system, forget getting the thing unpicked.
Well,
I'm not adding to your.
That's a different conversation. But I'll simply say that actually there are many aspects in North America that are much less capitalistic than people think. Let's leave it at that. I entirely agree.
Okay, I'm staring.
Yeah. No, that's perfectly fine. But like I say, that's a different seminar. That's a different discussion.
But when you say North America, I mean, the Canada system works the same as the US also?
The Canadian systems are province-based, and mostly they interact with the American markets. So Quebec, for example, has many more dealings with New England and New York than with the Canadian neighbors. So essentially Quebec is really a player in New York and New England in the market.
It would be a question of the transmission line length,
Yes.
nothing else.
Yeah, but that's where they are. That's where they mostly are, and that's what the dynamic is.
Yeah.
This is again a different talk in the sense, a different topic in the sense that what happens is that Canada is actually much more integrated vertically with the US than horizontally. It's always a battle to fight against the natural north-south connection. But certainly in electricity, that's where the connections are. The connections are mostly north-south, so that's the rules. There's a party going on outside? Yep. Very good. So everybody wants to move to 15 minutes. So that's becoming more of a challenge in this case. What I wanted to mention, and I'll just do it very briefly, is that we also looked at the issue of having symmetry in these problems. So if you have multiple generators that essentially have the same features, then you have to somehow deal with the symmetry that this introduces in the problem. And one straightforward way of handling it is to aggregate them into a big one, solve the commitment for the bigger one, and then disaggregate. But in practice, that can create some issues. So what we looked at was a way of taking advantage of the symmetry. And I'll just skip ahead a few slides to get to the basic idea. So this follows on some of the work that Jim Ostrovsky did on his PhD, where we have what's called an orbit of the problem. So this is a set of variables that essentially look the same from the optimization perspective. And I won't define exactly what that means, but in a sense they're undistinguishable in the optimization. And that's where symmetry comes from, because you can pick any one of them and the result is the same, but it increases the complexity of your decision making. So the original idea that Jim worked on his PhD was to say, well, instead of branching on one variable, 0 or 1, which can cause this very large growth of the tree, you can branch, because you have this special symmetric structure, by saying either they're all 0 or at least one of them is 1. And in at least a number of well-known difficult problems with symmetry, this works very well. This has a big impact on the size of the branching tree. Primarily because it fixes on the right a whole bunch of variables at the same time. It basically says the whole orbit has to be 0. And you've just eliminated a whole bunch of branchings. So we played with this for unit commitment and tried different ideas and came up with what we call modified orbital branching, which is essentially saying, well, instead of picking 0, 1, you can say, I want the sum of my x's to be at most b prime minus 1, or at least b prime. These are all 0s and 1s, so we're just deciding how many are 1. But by doing this change to the way you branch from the previous ones, you basically end up with a subtree that in many cases is more balanced. And in particular for the unit commitment problem, with multiple generators that are very similar, this makes a big difference in the computation. Comparisons get a little bit complicated. I just put a summary of the results here because there are things like, if we're going to compare with Cplex, then we have to use callbacks, but if we use callbacks, then it's not clear that it's a fair comparison anymore. But generally speaking, we did a bunch of tests that really suggest that modified orbital branching is significantly better than the original orbital branching. And sometimes the difference can be as much as 1 order of magnitude in the running times. But again, the comparison is difficult.
But do you, in the callbacks where it turns out dynamic branching?
Yeah.
So you're not. So can you beat dynamic sequence with dynamic branching with this? Or?
Yes.
So if you do this, it turns out that but with the orbital branching, it still beats the default.
It still beats the sequence. Yeah. But it's hard to know exactly by how much. And that's why it's hard. I mean, you beat, but you know, you say you beat by this much, but would it be even faster, or if you had the additional features? It's I feel a little bit uncomfortable with the comparison because you're not really changing just one thing, right? It's the usual. You're changing a bunch.
But if you beat sequence with that,
then it would. Yeah, it really.
But nobody does research in branching because you can't. It's so sophisticated. They turn off everything because they don't want you to reverse engineer.
Yeah.
What they're doing.
So for these problems, it seems to work very well when you have this kind of structure. Yeah. So that was basically the message for the second part. These are the references that I'll be very happy to pass on if you wish to look at them. And the bottom line is that even though this is a problem that has been around for a long time, it's still a challenge. There's a lot of work being done right now, stochastic versions especially, in particular to accommodate the integration of renewables into the system, because they have to be quote-unquote dispatched if you want to do a unit commitment, but you don't know what they are, so you get the uncertainty there. There's the whole impact of network effects that would be very interesting to bring into the picture. And ultimately, from a computational aspect, we want to get down to reliable solutions with 15-minute steps to really look at the reality of electricity markets at least in North America. And there are, I'll close by saying that this is one example of a problem in the power systems area that can benefit from optimization research, but there are others as well. There's a whole slew of problems in electricity, not only in markets, just in the power systems in general. There's a whole slew of problems that are essentially optimization problems, and there's potential to do lots of contributions to that area. And I'll stop there. Thank you.